This video is a quick overview of how standing waves are generated and some information about sound waves. If we want to produce a continuous sound, then we're going to need to set up something called a standing wave pattern. Last week we looked at traveling waves, or wave pulses, moving along a medium. Remember, the medium itself does not move, the energy propagates or travels through the medium. And so if we have a singular wave, whether it's transverse or longitudinal, we can see that it's sending the energy through the medium. And so that's what we call a traveling wave. This week we're going to be looking at what happens when that traveling wave is reflected or bounced back off of a fixed or loose end on the opposite side from where it was generated. And that standing wave forms, it's because that traveling wave reaches the far side, is reflected back, and then constructive and destructive interference generate this pattern that you see here, where we have changing amplitudes as the wave energy passes from left to right and then reflects back from right to left. And that's what's going to set up this standing wave pattern. So again, we have our traveling wave, it reflects back, and eventually we'll set up a standing wave pattern. Now, not all string lengths or frequencies will create this pattern. It will only exist at specific ones, and we're going to get into that in another video today. Now, there are two parts that make a standing wave unique. A standing wave is going to have antinodes, which are these areas of maximum amplitude or constructive interference, where both wave pulses, their amplitudes add, and it's going to maximize that value. And then destructive interference is going to happen at what we call the nodes. So these points right here, where it looks like the waves are crisscrossing. Now, in reality, this wave is not in two places at the same time. This is like a shadow of where it was before. So it will oscillate or move back and forth between the maximum amplitude and the minimum amplitude over time. Now, these nodes are going to remain areas of complete destructive interference. And so these points on the wave are going to appear to not move at all. So again, we've got antinodes, or areas of maximum amplitude and constructive interference. And then nodes are areas of zero amplitude, so they're on the equilibrium line, and they're caused by complete destructive interference. So in our study of standing waves this week, we're going to look at how they form on strings, and then we're also going to look at how they set up on columns of air. So we're going to be looking at standing waves on strings, as well as standing waves in air. Now, before we get into the structure of those standing waves on strings and air, there are some things that influence the speed of sound, and those things are the medium's density. So whatever the wave is traveling on, how dense it is going to impact how fast the sound waves travel. If it is less dense, then the energy is going to travel through that medium a little bit slower. If it is more dense, then it's going to travel faster. We should have seen that in last week's activity at the wave stations, that the student who heard the explosion, they had the speed of sound was a little bit slower through the air, so they didn't recognize the explosion until a little bit after the student who sensed the vibrations traveling through the earth, because the earth was more dense than the air. The other factor is temperature. So the warmer the temperature is in a space, the quicker or faster those sound waves are going to travel. And it's about 0.6 meters per second faster or slower for every 1 degree Celsius change in temperature. So at 0 degrees Celsius, the speed of sound is 331 meters per second. So a classroom is typically around 20, 21 degrees Celsius on a given day. Again, if your classroom's a little bit warmer, it might travel a little faster. If it's cooler, a little slower. And so that temperature would be around 344 meters per second for the speed of sound. So again, it fluctuates based on temperature. So by knowing the temperature of a space, you can approximate how quickly sound waves should travel, which will be helpful for the activity we are going to be doing this week. Now in the following videos, we're going to look at how standing waves are set up on strings, depending on a tightly stretched string, that is. That one would have high tension, and again, we looked at how tension affected wave speed last week in the activities. We're also going to look at how standing waves would form in percussion instruments such as drums, as well as wind instruments where you have columns of air that are either opened or closed or have one end open, one end closed, as well as our voices. So that is what's coming up in these videos this week.